So in this video, we'll be going over how to draw free body diagrams for the following situations. So as with everything, the first thing you want to do is define your coordinate system. So looking at this first top picture here, we've got this roller coaster cart that's traveling along the track, and that track makes this circular shape to it. And so the motion along that arc can be described as circular motion. Since the cart's going to be going up and down, we're not going to define a Y direction. We're going to define an R direction, and we're going to define a T direction for the tangential direction. So the first step is you want to find your circle, which we already have here. And so we need to define our radial or our centripetal direction. And so drawing from point A, we draw inwards towards the center of the circle, and we'll call that the positive R direction. You can draw the other way, being the positive R direction. It doesn't really matter as long as you stay consistent, but it will make your life easier just to draw the R direction as towards the center of the circular motion. The next step we need to do is to find the T direction. The T direction is always going to be perpendicular to the R direction. So in this case, it's going to go out to the right from point A. That is perpendicular to the R direction. And we're going to call to the right the positive T direction. So now that we have that, we can draw our free body diagram. How many forces are acting on the cart at point A? So that's the first thing we need to ask ourselves. There's obviously going to be a weight force. Gravity is going to be pulling that cart downwards. And then we need to figure out what, if any, are the other forces. The cart's in contact with the track. So the track is going to be pushing up on the cart. So gravity is going to be pulling downwards, and the track is going to be pushing upwards on the cart. And that upwards force is the normal force. So we have two forces acting at point A. So we're going to start by drawing the weight force. That's going to be pointing downwards. W, we'll just call this cart M. And so if you want to, you can just call that mg for weight force, but you can just leave it as W. And then the normal force, the force being applied to the cart by the track, is pointing upwards. But is it the same magnitude as the weight force? For that, we need to think about the acceleration. What's happening in this situation? The cart can be described as this uniform circular motion. So we know that velocity is changing direction. This tangential velocity over here is pointing this way. This tangential velocity here is pointing this way. So if we have a velocity that's changing, we know we have an acceleration. And the acceleration is going to be pointed inwards towards the center of the circle. So at point A, we have an acceleration that's pointed inwards, which tells us that we need to have a net force that is pointing inwards. So to make that happen, the normal force needs to be of greater magnitude or a longer length than the weight force. So F sub n. And that tells anybody that there's going to be a net force or an acceleration in the positive R direction. So now to get more practice, we'll go to the second one. We're going to apply the same sort of logic for point B here. So again, we're going to choose from point B the direction inwards towards the center of the circle to be the positive R direction. And then to the right, tangent to point B, and perpendicular to the positive R direction to be the positive T direction. And so we just do the same sort of thing again. Which way is the direction, which way is the acceleration's direction for this part? So we know that for point B, the acceleration is going to be pointed inwards towards the center of the circle. So we need to have a net acceleration that's pointed inwards in the positive R direction. So coming over to our free body diagram, upwards this time is now negative R, and downwards is positive R. And to the right is still staying the same as positive T. We're going to start by drawing our weight force. Our weight force is going to be pointed downwards in the positive R direction. Weight force. And now, which way is the normal force pointing? Is the normal force pointing downwards, or is it pointing upwards? And so the normal force is still the force that the track is applying to the cart. And so that's going to be pointed upwards. So that, you have your cart right here. It's on the track's pushing upwards. And so it's still going to be pointed upwards, just like in the first part. Now we need to determine what the magnitude, how long should we draw this normal force vector? We know we need an acceleration towards the center in the positive R direction, which is downwards. So the magnitude of the normal force needs to be smaller than the weight force, so that we have a net force in the downwards or positive R direction. And so we have experiences with these forces. If you've ever been on a roller coaster, or if you've driven over a hill or under or down a hill, then you know that you can experience feeling lighter or heavier than you otherwise normally would. So let's take a look at 2 again for situation for the position B. And let's try and make sense of it. So we're at the top. We have a net force downwards, so the weight force is greater than the normal force. And so since the normal force is less than the weight force, it's smaller than what we would normally experience if we weren't accelerating. So we're feeling lighter or less heavy than we normally would. And the reason why is that cart is not pushing up on us as much as it would if we weren't accelerating. So it makes us feel like we're lighter than we actually are. And then the opposite for A, the normal force is greater than the weight force. So that normal force is pushing harder on us. And that's that idea of a G-force that you get for if you're like an airplane pilot, where you're feeling pushed down into your seat more. That's because of this normal force that's greater than what it would normally be if you were stationary. So if the next time you're driving down a large hill, pay attention to how you feel at the bottom of the hill. So if you got something like this and you start to go back up, pay attention to this spot right here and see how you feel. Do you feel heavier? And then you can use these forces to explain why you feel heavier at that spot.